Good day to you all. This is Students ScoreBooster series video for WAEC, JAMB and other SSC exams. Today we have come again with chemistry, and the topic we are going to treat is on the last topic that we treated, with atomic structure the last time, and it's still going to be your same instructor, Latif. Today we are going to study electrons, because the last time we said that the atom is made up of one central core that is composed of neutrons and protons. An electron is revolving around it. That makes the complete description of atom. And we study the nucleus last class. But today we are going to study electron. What makes this study important? It is because of some other topics that we are going to treat later, like periodicity and periodic table, shape of the molecules, chemical bonding. Each of these topics require the knowledge of where electrons are located. That is why it is worthwhile to treat electron itself as a whole topic, such that we will not be found wanting when we get to those areas. It is our hope that after this video, students should be able to describe the 4 quantum numbers and be able to name and draw them. Then we have insight into writing the electronic configurations of the element. Last time we presented this diagram as a structure of atom, where we have protons and neutrons at the center, then electrons are rotating around it randomly. Scientists later discovered that this random description of electron moving around the nucleus is not enough, because complete description of where electrons are located is not random. So in that case, a quantum mechanical model is now used to describe the location of electron. This random quantum model is highly mathematical, although we are not interested in the details of the mathematics involved. It's highly mathematical, and it states the position and momentum of the electrons. It is also called uncertainty principle of chemistry. Scientists developed this concept of orbitals because we said last week that the electrons are revolving around the atom, which is partially correct, not completely correct, although they are moving around the nucleus of the atom, but at a particular location called the orbital. Those orbitals are the place, are the volume of space where electrons are found, where electrons are present. You cannot just locate electron outside the nucleus. That is what this statement is trying to tell us, that there is a particular place where electrons are found. All those places are called orbitals. And in describing this, we have 4 quantum numbers, which is the number 1 there is the principal quantum number, designated as n. This small letter n is used to represent the principal quantum number. The second one is the angular momentum quantum number. It is also called Azimuthal quantum number. The next one is the magnetic quantum number, that is m. Some books they use ml or m subscript l, but let us make it simple here by using our m. Spin quantum number, it is represented as s. So let us now take them one after the other. This table summarizes each of them. This principal quantum number is represented as n and describe the energy of the orbitals. What we are trying to say is this: the energy of the orbitals, because elements, atoms, they have different sizes. Some contain 1 orbital, some contain 2, some contain as much as 5. We should not forget what we learned from Niels Bohr that time, last week, that electrons are located in an orbital of equal energy. If there's a misplacement or by accident electron found itself in a place where its energy is more than the energy of the shell, so it quickly jump up to where its energy is equal. So the available values for this principal quantum numbers are integers. We should not forget integers are whole numbers, and it has to be positive, like 1, like 2, 3, and so on and so forth, like that. Angular momentum quantum number, it is L, and it describes the shape of the orbital and possible degeneracy of the orbital. We will learn more about that later. And the integers is from 0 to n-1. The value of L is dependent on the value of n here, because as you can see from here, it is 0 to n-1. If n is equal to 1, that means we have only 0. If n is equal to 2, we have 0 and 1. If n is equal to 3, we have 0, 1, and 2, and so on like that. So there is no way the value of L will be more than the value of n. The angular momentum quantum number is dependent on the principal quantum number. So it is not possible that we have a value of angular momentum quantum number greater than the principal quantum number. So the magnetic quantum number describe the orientation of the orbitals in space, because from the angular momentum quantum number we said that it describes the shape and the degeneracy of the orbitals. The way some orbitals degenerate, some don't. Those that degenerate, the way they orientate themselves in space are different. That is why we have the magnetic quantum number, whose value is dependent on the value of angular momentum quantum number L. This is not confuse this one. This one is L, not L. This is L, not 1. This one is 1. This one is L. The value of M is -1 through 0, then to plus minus L through 0, then to plus. It is, I would have used a capital letter L, but the registered letter is small letter L. So what we are saying is this: if we have only 0 as our L from here now, so M has no option than to be equal to 0. If we have 1 from here, that 0 and 1, so M will be -1, 0, then +1. If we have 2 here now, M will be -2, -1, 0, +1, and +2. So we have 5 generated orbitals like that. So spin is just 2 plus half or minus half. It is either electron is spinning clockwise or anticlockwise. So let us now take them one after the other. Principal quantum number describes the average distance of orbitals from the nucleus. It also describes the energy of the electron in an atom. We have explained that one before. The distance of the orbitals from the nucleus is dependent on the quantum number. If we have n is equal to 1 and n is equal to 2, the meaning of it is that the orbital that has n is equal to 2 is farther away from the nucleus than the other one whose the value is equal to 1. It also describes the energy of the electron in an atom. The electron that is in the closer orbital is of lower energy than the electron that is farther away from the nucleus. That is what this statement is trying to tell us. The higher the value of n, the higher the energy and the larger the orbital, as we have discussed before. It can only have positive integer value. That n is equal to, can be equal to 1, 2, 3, 4, 5, and so on like that. There's no circumstance that which n can be equal to negative, because it describes the energy which is real, so it can't be a negative value. And the larger the value of n, the larger the size of the orbital, and the greater the distance of the orbital from the shell. The angular momentum quantum number, that is also called the azimuthal quantum number, describes the shape of the orbital. When we have a particular orbital, value of L tells us which shape is it. Then the value is limited by the value of n, as we have said, because the formula is L can have a formula from 0 to n minus 1. So the value of L is dependent on the value of n, principal quantum number. So if n is equal to 2, L can be equal to 0 and 1. If n is equal to 3, L can be 0, 1, 2. We should note that the value of L defines the shape of the orbital, and n defines the size, as we have said before. The size of the orbital is determined by the value of the principal quantum number, which is n. Then the shape is determined by L. Orbitals that have the same value of n but different L values are called subshells. These are given later for easy recognition. There are many subshells that we have, because we say that it describes the shape and possible degeneracy of a particular orbital. If in a particular orbital now, let's say 1, and there is degeneracy, maybe that one now degenerates into maybe 3 places now. So we cannot use a single letter for all those 3 places, because as we will learn later, there is energy associated with each of these orbital and subshells. So to differentiate, for proper differentiation of each of them from each other, so scientists agreed on using letters for recognition. So these are the letters. When L is equal to 0, the letter of the subshell is equal to S. It's called S. When L is equal to 1, P. When L is 2, D. When L is 3, F. When L is 4, G. For now they are using G. S, P, D, F, G. It doesn't mean that L cannot be 5. If L is 5, then they will use another letter. But for now, 4 is enough to describe any element. If they now discover another element which require the value of L to be equal to 5, then they create another letter. But for now, they have not done that. Complete shell specification is done by specifying the values of N and L. So if you want to specify a shell now, the value of N and L are put close to each other, like we have 2s, like we have 3p here. 2s means that N is equal to 2, that is the principal quantum number. When N is equal to 2, it means this particular shell that we are seeing is on the second energy level, the second shell. Then this subshell is S. So in that case, L is equal to 0 here. We will see examples. 3p also. We have 3, the energy level 3. Then we have p. P means our L is equal to 1. In that place, we should not forget that the value of L is equal from 0 to n minus 1. So these are the shapes of the subshells that we have. This one is S. This one is another S, S and 2S. That's what we are saying about the size and the principal quantum number. This one is 2S. The two of them are S, the same shape, but this one is on the second energy level, this one on the first. That means if we are to nestle this in this 1s into 2s, we are going to see that this one is smaller than this. 1s is smaller than 2s. It means that the energy of this one is less than the energy of the 2s, and the distance of the 2s is greater than the distance of the 1s. They have the same shape, spherical shape. S stands for spherical. Here we have P, Py, Px, and Pz. The shape is dumbbell shape, and we have seen the orientation. This one is going towards y, this one is going towards x direction, this one is going towards z direction. These are the degeneracy that the value of L gives us. When L is equal to 1, we have P. So this one is D, double dumbbell. We can see that it looks like dumbbell. This one is double of it. That's why we are seeing square, dz square. This one is dx, x direction, and z direction. You can see x direction, this one is y direction, so dxy. So this one is the same double dumbbell. We have two dumbbells, that is why we are having double dumbbell. So let's go to magnetic quantum number. The orientation of the orbitals in space is described by this quantum number, and the values depends on value of L. So m is from minus L to plus L. That means if L is equal to 1, m can be minus 1, 0, and plus 1. If L is equal to 2, m can be minus 2, minus 1, 0, plus 1, and plus 2. This means that there are, this example that we did, it means there are 3 p subshell, because L is equal to 1. And here, from L is equal to 1, so we have p. So there are 3 p subshell for a particular orbital. So each of the orbital that we have 3 p subshells. These subshells have the same energy but different orientation in space. P, all the p's that are in the same orbital, they have the same energy. What I mean is 3p, all the 3 p's have the same energy, all the 4 p's have the same energy, all the 5 p's have the same energy. But 5p is not of the same energy as 4p. 4p is not of the same energy as 3p, and 3p is not of the same energy as 2p. There's no 1p. So if we have 2 now, 2 is equal to d. 2 we have minus 2, minus 1, 0, 1, 2. So we have 5. So that means the degeneracy of d is equal to 5. Like we have 3 in p, so d is equal to 5. But as you can see, s cannot be minus 0, 0. So we have only x. So that's why we are seeing x. We cannot see x, 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 y, x, z. So but p we have 3, we can have px, py, and pz depending on the orientation in space. Spin quantum number. Spin is just spin. Something like rotation. It is not actually rotation. It is spinning. I don't know how to describe it. It describes the direction of spin of electron in a magnetic field. It is either clockwise or anticlockwise. Clockwise is positive, anticlockwise is negative. So only 2 values are allowed, which are minus half or plus half. Somebody will ask me, why not minus 1 or plus 1? It is simple mathematics. The occurrence of 1 out of 2 possible options, that is 1 over 2. Probability of being in the clockwise direction is 1 over 2. The probability of in the anticlockwise direction is 1 over 2. So they just use this minus to indicate that the directions are different. You should note that for each subshell there can be a maximum of 2 electrons, one with plus half and the other with minus half. What we are saying is this: if you have a particular subshell here, like 1s, there can be 2 electrons maximum. It doesn't mean that there cannot be 1. There can be 1, but there cannot be 3 in the x subshell. So when we have s also, so far it is s, it is half. If it is p also, each of the subshells in p, minus 1 is a subshell, 0 is a subshell, plus 1 is a subshell. So each of them now contains 2 electrons. So we have 6 electrons totally in 2p. So if we have d also, and d is equal to 5, generation as we said before, minus 2, minus 1, 0, 1, and 2, and each of these can contain 2, it means that d can contain the maximum of 10 electrons. So f like that, g like that. We can do that from this table to determine the number of electrons that can be there. S has maximum of 2 electrons. It is immaterial. It is not dependent on whether it is 1s or 2s or 5s. Even 5x and 1s, they contain the same number of electrons. The maximum of electrons is 2 in s. The same thing as p, the same thing as d, the same thing as f. What we are saying is this: 1s contain 2 electrons, 2x contain 2 electrons, 3x, 4x, 5x, they contain 2 electrons. P must contain 6 electrons, maximum of 6. It can contain 1, 2, 3, 4, 5, depending on the element that we are considering. But it cannot contain 7. So, and it doesn't mean that this one is 2p and 3p must contain more than 2p. No, 3p and 2p, they contain the same number of electrons. That is what we are seeing. So, in summary, there are 4 quantum numbers, and they are collectively used to specify the position and energy of a shell as well as the shape of the orbitals. There are letters that are used to specify the orbitals: S, P, D, F, etc. And this table summarizes what we have been seeing before. When L is equal to 1, L can only be 0, M can only be 0, and then the orbital that is equal to 0 is S. So when N is equal to 2, L can be 0, 1, so M can be minus 1, because the value is from minus L to plus L, minus 1, 0, and 1. So 1 is equal to P as we saw it there. S is equal to 0, that is there. So D is minus 2 here. 1 is the other one. 0 is for spherical shape. So this is what we have for today, because the knowledge of this SPDF notation is actually useful when we are to write the electronic configuration. And what we have learned about this will now be transferred to the next class, which is on the energy level diagram representation of the atom, because each of the shells, they don't have the same amount of energy. So we are going to determine that, then the principle that we are going to derive from it will be used to write the electronic configuration of the element. The exercise is number 1. Using the table 1.1, determine the 4 quantum numbers for an atom with energy levels n is equal to 3 and 4. Then find the maximum number of electrons each of the shell can contain. Write the name of the shape of this. You have to write the name because the shapes have been drawn before. So you are just to write the name. I've mentioned the names more than once, more than twice in this lecture. So just write the name and practice it. Practice the exercises. So this is the answer in case you want to check after trying it. So thank you very much for listening, and this is just the brief curriculum vitae of the instructor. Thank you for listening.